Direction cosines of the coordinate axes. To start, let's recall what we have covered so far in our study of three-dimensional geometry. We have already learned that if we want to uniquely determine the direction of a line in space, we can use what are known as direction cosines. Now, what exactly are these? Simply put, these are the cosines of the three specific angles that a given line makes with the positive directions of the x, y, and z axes. Now, you might be thinking that calculating these angles for any random line in space could get quite complicated, and you are right. Most lines in 3D space do indeed make very complex angles with the axes. However, today we are going to look at the simplest possible cases, the coordinate axes themselves. Because the x, y, and z axes are mutually perpendicular, or what we call orthogonal, their direction cosines are not complex. They are fixed, simple values. Understanding these specific values is fundamental, as they will serve as the building blocks for all your further calculations in 3D geometry. In the next few slides, we will walk through the step-by-step process of calculating these values for each axis. Welcome, everyone. Let's begin our lesson on the direction cosines of the coordinate axes. Understanding the concept. Now that we have established what direction cosines represent in a three-dimensional space, let's look at the actual process of finding them. To find the direction cosines of any specific axis, we need to perform a simple three-step measurement. We must determine the three specific angles that the axis in question makes with the positive x-axis, which we call alpha, the positive y-axis, which we call beta, and finally, the positive z-axis, which we call gamma. Once we have identified these three angles, alpha, beta, and gamma, the direction cosines themselves are simply expressed as the set containing the cosine of alpha, the cosine of beta, and the cosine of gamma. In the next few slides, we are going to apply this exact method to the x, y, and z axes one by one to see how these values emerge. Direction cosines of the x-dollar axis. Now that we understand the general concept of how to find direction cosines, let's apply it to our first specific case. Let us consider the x-axis itself as our directed line. To find its direction cosines, we'll follow a simple four-step process. Step 1, we look at the angle the x-axis makes with itself. Since they are the same line, the angle is 0 degrees. Therefore, alpha equals 0 degrees. Step 2, next, we look at the relationship between the x-axis and the y-axis. Because the coordinate axes are perpendicular to each other, the angle between the x-axis and the y-axis is 90 degrees. This means beta equals 90 degrees. Step 3, similarly, the x-axis is also perpendicular to the z-axis, so the angle gamma equals 90 degrees. Step 4, now we simply calculate the cosines of these three angles. We have cosine of alpha, which is cosine of 0 degrees, which equals 1. Then, we have cosine of beta, which is cosine of 90 degrees, which equals 0. And finally, cosine of gamma, which is cosine of 90 degrees, which also equals 0. As a result, we can conclude that the direction cosines of the x-axis are 1, 0, 0. Direction cosines of the y-dollar axis. Now that we have successfully determined the direction cosines for the x-axis, let us apply that same logic to the y-axis. We will treat the y-axis as our primary directed line and find its relationship with all three axes. First, let's look at step 1. We need to find the angle alpha, which is the angle the y-axis makes with the x-axis. Since the coordinate axes are mutually perpendicular, this angle is 90 degrees. Therefore, alpha equals 90 degrees. Moving to step 2, we consider the angle beta, which is the angle the y-axis makes with itself. Just like we saw with the x-axis in the previous slide, the angle an axis makes with itself is always 0 degrees. So, beta equals 0 degrees. In step 3, we find the angle gamma, which is the angle the y-axis makes with the z-axis. Again, because these axes are perpendicular, this angle is 90 degrees. Thus, gamma equals 90 degrees. Now, for step 4, we perform the actual calculation by taking the cosines of these angles. First, the cosine of alpha, which is the cosine of 90 degrees, equals 0. Next, the cosine of beta, which is the cosine of 0 degrees, equals 1. And finally, the cosine of gamma, which is the cosine of 90 degrees, equals 0. As a result, we can conclude that the direction cosines of the y-axis are 0, 1, 0. This pattern is very similar to what we found for the x-axis, and we will see a very similar result for the z-axis in the next slide. Direction cosines of the z-dollar axis. Now that we have successfully determined the direction cosines for the x-axis and the y-axis, let us complete our set by looking at the final axis. Finally, let us consider the z-axis as our directed line. To find its direction cosines, we will follow the same systematic approach we used in the previous slides. Step 1. We look at the angle the z-axis makes with the x-axis. Since these two axes are perpendicular to each other, the angle is 90 degrees. Therefore, alpha equals 90 degrees. Step 2. Next, we look at the angle the z-axis makes with the y-axis. Again, because they are perpendicular, this angle is also 90 degrees. So, beta equals 90 degrees. Step 3. Now, consider the angle the z-axis makes with itself. Since it is the same line, the angle is 0 degrees. This means gamma equals 0 degrees. Step 4. Now, we simply calculate the cosines of these angles to get our values. First, cosine of alpha, which is cosine of 90 degrees, equals 0. Second, cosine of beta, which is cosine of 90 degrees, also equals 0. And third, cosine of gamma, which is cosine of 0 degrees, equals 1. As a result, we can conclude that the direction cosines of the z-axis are 0, 0, 1. This pattern we've seen across the x, y, and z-axes is very consistent, and in the next slide, I'll show you a real-world way to visualize why these values make perfect sense. Real-world analogy. Imagine for a moment that you are standing right in the corner of a room. This corner is the perfect place to see our three axes in action. Look at the floor where it meets the left wall. We can think of that line as our x-axis. Now, look at the floor where it meets the right wall. That line represents our y-axis. Finally, look straight up at the vertical line where the two walls meet. That is our z-axis. Now, let's apply what we just learned about the direction cosines. Suppose you decide to walk exactly along that line where the floor meets the left wall. Because you are walking strictly along that line, you are moving entirely in the x direction. You aren't moving across the room toward the right wall, so there is no y component, and you aren't moving up the wall, so there is no z component. This is exactly why, as we saw in the previous slides, the direction cosines for the x-axis are 1, 0, 0. The entire strength or magnitude of your movement is concentrated solely in the x component, leaving the other two values at 0. This simple visualization helps us remember why the axes always result in such clean, simple values. Now, if all those mathematical steps and calculations feel a bit abstract, let's ground them in something you can actually visualize. Key takeaways. First, it is important to recognize that the direction cosines we just calculated for the coordinate axes are actually the most basic unit vectors in three-dimensional space. They represent the purest form of direction without any deviation. To recap our findings, for the x-axis, the direction cosines are 1, 0, 0. For the y-axis, they are 0, 1, 0. And for the z-axis, they are 0, 0, 1. A very important point to remember is that these values must always satisfy the fundamental property of all direction cosines, which states that L squared plus M squared plus N squared equals 1. We can easily verify this with the example we just found for the x-axis. 1 squared plus 0 squared plus 0 squared equals 1. Now that we have worked through the step-by-step derivations for the x, y, and z axes, let's bring everything together for our key takeaways. As we move to our final slide, I will point out some common pitfalls to avoid when working with these values in more complex problems. Common mistakes. First, watch out for the incorrect order of values. It is very easy to get mixed up when writing down your final coordinates. Always remember that the sequence must strictly follow the order of alpha, beta, and gamma. In other words, the set is always cosine alpha, cosine beta, cosine gamma, which corresponds directly to the x, y, and z axes respectively. If you swap them, your entire vector will point in the wrong direction. Second, be careful not to confuse sine and cosine. When you are first learning 3D geometry, it is tempting to use the sine function, but remember, as the name implies, we are specifically looking for direction cosines. As we saw in our calculations for the x, y, and z axes earlier in the presentation, using the cosine function is what gives us those clean, simple values of 0 and 1, because cosine of 90 degrees equals 0 and cosine of 0 degrees equals 1. Finally, do not assume that all direction ratios are direction cosines. While it is true that for our coordinate axes, the values 1, 0, 0 act as both direction cosines and direction ratios, this is not a universal rule. The key distinction is that direction cosines must always satisfy the property where the sum of their squares equals 1. As we noted in our summary slide, L squared plus M squared plus N squared must equal 1. Direction ratios can be any set of numbers that maintain the same proportion, but only direction cosines have that specific magnitude of 1. Now, before we conclude our lesson, I want to touch upon some common pitfalls that students often encounter when working with direction cosines. Paying attention to these will help you avoid losing marks in your exams. Keep these points in mind, and you will have a much stronger grasp of 3D vectors.